Okay. Good morning, and first of all, let me join the other speakers in thanking the organizers for organizing this wonderful conference, and also for having me part of it. I'm enormously enjoying the conference, and it's definitely a great honor for me to present our work here. My talk will be in the field of multi-particle entanglement, and I'll present two different methods of creating many particle entangled states in ensembles of cold atoms. Well, entanglement, of course, has always been of interest to quantum physicists, but recently there has been this notion of entanglement as a resource. And indeed, if you look at the list of quantum technologies that we know so far, almost all of them critically rely on entanglement. What I talk about is methods that, modestly, don't attempt to be universal, like the spectacular ion trap experiments that we've seen yesterday, but instead try to produce a given state in a way that potentially can be scaled up to larger atom numbers. And in the first experiments that I show, a cavity is used to implement an interesting, conceptually interesting method called quantum xenodynamics. While in the second part, I'll show you an experiment that produces spin squeezing in a rubidium BEC in a very straightforward way. So we will use just the simplest possible case, two-level atoms. We have n two-level atoms, and as you know, they can be, they're symmetric states where all atoms have equivalent roles, can be represented as an effective spin in halves, which then can be represented on a Bloch sphere. In the following, it will be useful to use the base made up of so-called Dicke states, the equivalent of Fock states in optics, which have well-defined numbers of excitations. And we note in passing that all of these states, except the one with 0 or n excitations, are themselves entangled states, but because indeed, although each of the atoms has a probability for being spin down or spin up, when you measure them collectively, they conspire so that the number of excitations that you measured is a well-defined number with no fluctuations at all. So let me come to the first topic, quantum xenodynamics. So quantum xenodynamics is a really fascinating concept that has been theoretically explored for quite a while now. So suppose you have a Hilbert space in which you can do some form of coherent driving, and so you create states, but maybe the states that you can create are not yet the ones that you would like to do. You cannot do everything. However, you have a second resource, which is doing a measurement, and this measurement should be such that it distinguishes some subspaces in your Hilbert space, but within each of the subspaces, it does no damage so that coherence is preserved. Then what happens is that you will get new states as you continue your coherent driving. Now the dynamics will be different as the state approaches this boundary, which it cannot cross because of the measurement. And if we do that in the concrete case of our spin and half system here, and let us suppose that we measure out this state here on the equator of the Bloch sphere. So if you start at one of the poles, you do some coherent driving, then the system cannot cross the equator because the measurement continuously reduces the probability for that state to 0. And so looking at the Bloch sphere from the pole, here's a numerical simulation of what will happen in such a case when you just drive a good old Rabi oscillation in such a system, but simultaneously you block the equator by measurement. So sorry for the black stripes. So here, as it approaches the equator, you see that it goes through a state where it's as if it was reflected here, and at this particular moment, then you actually have a phase cat. And that happens due to the presence of the measurement on the equator. Here's another example. If you measure at the pole, and suppose you start at the opposite pole and drive again, just a Rabi oscillation. Here's what you would get. Once again, we look at the pole, we look at the Bloch sphere from above, we look at the point that is being measured. And the distribution comes up from the south pole, and as it approaches the north pole, it can't reach it, it goes around it, and then at the moment it reaches or it would reach the pole without the measurement, oops, if I had stopped it at the right moment, at this particular moment, you see that your distribution has this this strange ring shape, and actually at this point in time, it is very close to the first Dicke state, the state with just one excitation, also called the W state, which is an entangled state where you have exactly one excitation, but which is distributed over all the atoms. Now, what we have in the lab is a fiber-based high-finesse cavity that indeed allows us to do a fairly good approximation of non-destructive measurement in the following way. I mean, we have our ensemble of two-level atoms. We tune the cavity with a piezo, and inside the cavity we have an ensemble of atoms which is trapped, all atoms trapped at a single antinode of that cavity using this atom chip here. We get fairly high cooperativity in the system due to the use of very strongly curved mirrors that we produce by CO2 laser machining directly on optical fibers. So this optical fiber cavity here has a length of 38 micrometers and has these parameters here. The finesse is not even state of the art anymore. But anyway, this cavity is good enough that when you detect at a pole, so in the following experiment, we will use the experiment tuned to this red transition here. That would mean that you can that your cavity always transmits, always reflects, except in one case, the case in which all atoms are spin down. Because as soon as you have one spin up here, then you get the vacuum Rabi splitting, which detunes the cavity from resonance. So a laser beam resonant with this transition will no longer be transmitted and will be reflected. So actually, what this cavity does in that case, it tells apart the state with all spin down from the ensemble of all other states. So this will be our Hilbert subspace. And in this subspace, there's almost no spontaneous emission, so that if we apply a coherent drive between these two states here, we can get coherent dynamics within that subspace. So once again, what we do is this. The cavity detects here the south pole, tells it apart from all other states. And if we were to start in that state, then we would just get the well-known quantum Zeno effect. The system could not leave that state because it's being measured. But that's not what we do. Instead, we start at the other pole of the cavity, so of the Bloch sphere. So all the Bloch sphere is accessible to the atoms, except for this one point at the south pole. And we drive a microwave pulse that would bring the atoms to the south pole, except that they can't reach it. And so maybe coming back to my cartoon picture that I started with, in that case, maybe a more appropriate way of representing that would be this. This is our Hilbert space. There's one point here that is blocked by the measurement, and the system evolves here, and usually it would just evolve in some straight line that symbolizes a coherent state. But because of the measurement, dynamics is modified, and as you approach this forbidden point, you get entanglement. And here now are experimental results. What you see here in this upper row is a quantum tomography, also performed with a cavity, near the south pole. The south pole of the Bloch sphere is here, you see in the middle. So essentially, from this, we get the full information about the quantum state, the symmetric part of the quantum state, and also we get the probability of being in that symmetric subspace. So we get a quite complete information about our quantum state, and we can do a maximum likelihood reconstruction from it, which you see in the lower row. And you see here close to the pi pulse time, you indeed get such a structure that has a hole in the middle. And now the question is, okay, so how good is it? Well, if we calculate the fidelity with the W state, it's 37%. Well, is that good? Is that not good? Well, actually, in order to have something a bit more quantitative, we applied an entanglement depth criterion, which shows that in this state, in order to get this tomography information, by the way, more precisely, this is what we are measuring here is the Husimi Q distribution. So in order to get this Husimi Q distribution here, we need to have at least 8 entangled atoms in our ensemble of a total of 40 atoms that we are working with. So definitely it can be improved, but also definitely it has created entanglement using this method, which I find kind of interesting. And the question is, what is it limited by? And the limits does come from spontaneous emission. So here's the trade-off. We are detecting with light, and although most of the time there's almost no light in the cavity because the cavity is reflecting, as you get to the pole, intensity in the cavity does increase a little bit, and then there's some probability for spontaneous emission. And you can reduce that by reducing the intensity of your probe beam, but that means that you are also reducing the effective measurement rate. And so there's a compromise to be made here. Well, if you measure too infrequently, then of course the xenodynamics is no longer perfect. I mean, the blocking of the state is no longer perfect. On the other hand, if you probe too rapidly, then you get too much spontaneous emission, and that's what we see here. When this here is the measurement rate, so essentially it's the intensity of the probe beam, and this here is the probability in being for reaching our target state, the W state. And here you see also that the population of the symmetric subspace goes down as faster and faster as the more you probe. So it turns out, okay, so why do we get this spontaneous emission? Although our cavity cooperativity is so high, it turns out that we are actually not limited by our cavity cooperativity. We are simply limited by the fact that our cavity happens to have an orthogonally polarized second mode that is very near the mode that we are working with. And that creates actually additional spontaneous emission via a Purcell-like effect. So just by eliminating cavity birefringence and there's a zero missing here, and going to the state-of-the-art finesse of 200,000, we calculate that we should be able to get a fidelity of 80%. So that's the state of this experiment. So now work in the lab focuses on building a better system with a better cavity, and we will also at the same time add a simple poor man's quantum gas microscope in the same system, which should allow us to observe the single sites in the cavity. Another interesting prospect here is to do this kind of experiment with an optical qubit instead of a microwave qubit, because then you can use essentially infinite cavity detuning and thus reduce spontaneous emission and completely eliminate this as a limiting factor, which also sounds interesting. Another perspective for cavity experiments, I mean, as Vladan Vulicic has shown in a series of groundbreaking experiments, there are several ways the cavities can be used to produce spin-squeezed states, and which are perhaps the most important resource for quantum-enhanced metrology. And this is something that now I think must be taken to the real metrological level. There have been proof of principle experiments that indeed show that you can improve a clock by spin squeezing, but not yet at a level that is of metrological relevance. And we have a test bed in collaboration with the French time and frequency metrology laboratory, the CIRT, where we have an experiment that is an atomic clock on a chip. It's not a super duper clock, but it is a little bit better now than the best commercial rubidium clocks, the ones that are also in GPS satellites, for example. It has 1 second stability in the mid 10 to the minus 13 range. And it works with trapped atoms, which is typically the kind of situation where squeezing would be interesting, because it's not easily possible to increase the number of atoms. So you need another way to increase, to improve your stability. And on that system, we would like to implement cavity-based squeezing. So we have now set up the hardware for that. Here you see the brand new atom chip for the clock with a fiber cavity on it. And we are now in the process of putting that into vacuum and building an experiment with that. So in my remaining time, I'd like to show you an amusing little experiment which we have performed on the platform of this TAC experiment. So which is basically an atom chip-based experiment where you can create BECs, but also it has all the benefits of metrology. It has a mu metal shield, and it's connected to a state-of-the-art local oscillator and all that. And here we are now creating spin-squeezed states in a way that is completely different, doesn't involve cavities, and that has been known for a long time, but not completely realized maybe in the spirit of its original proposal. Here's the idea. I mean, it is known that in order to produce spin-squeezed states, that is, states where the noise is redistributed so that you have one coordinate, one axis along which it is lower than the standard quantum limit. You can create such a state if you can make this form of a Hamiltonian that is proportional to SZ squared. Because then you know, thinking again of our Dicke basis, now you have a force that depends on the Dicke state that you are in, and that creates some shearing on the Bloch sphere, and this kind of distortion would transform an initial coherent state into such a spin-squeezed state. Now there are several ways that you can produce this form of Hamiltonian, and actually it should naturally occur in BECs due to atomic interactions as soon as the interactions are not the same for the spin-up and the spin-down states. However, in rubidium, which is the most widespread element in atom interferometers and many metrology related experiments, it so happens that all these scattering lengths are almost equal. And then it turns out that this chi here is very close to 0, and that is why the simple idea of just doing a pi over 2 pulse and then letting nature produce the spin-squeezed state for you doesn't work out usually. And there have been very clever methods that have been devised to work around that problem, and spectacular results have been achieved by Philipp Treutlein's group, by using state-dependent potentials to, you do a pi/2 pulse, and then you separate the two components in a coherent manner, and by separating, you bring this cross term here to 0, and then you get the squeezing. So that has been done. Feschbach resonance has also been used, also with spectacular results in Markus Oberthaler's group. But of course, these methods come with additional complications in order to work around this problem here. Now, in our experiment, which I already mentioned, the experimental situation is like this. So we have a trapped condensate in a cigar-shaped trap with a very low longitudinal frequency, 2.7 Hertz. We use two states that have the same magnetic moment to first order. These are our clock states. And we use a two-photon transition to drive the transitions and create superpositions of these two states. And then what we do, we also have a very good detection system, but I no longer have time, I think, and so I skip that. Just let me tell you that the detection is close to the projection noise limit. And then what we do in the experiment is simply we do a pi/2 pulse on that transition, and then we wait. And then if we do a state analysis by measuring the noise of our coherent superposition by measuring N1 and N2, and we do that rotating the state, and for every angle we do this measurement in order to get this distribution here. Here's what we get. It's the familiar distribution of a spin squeezed state. And the spin squeezing that we get in the end, so this is the total here, then we zoom around zero angle here, you see that it goes down to 1.7 dB of metrological squeezing. So contrast already taken into account, the reduction of contrast that we have. So it's not very much squeezing, but there is some, and so what's the trick? Why do we get this squeezing just by letting the system evolve, in spite of the fact that the scattering lengths are so close? Well, the reason is simply this. In our, we have chosen our trap geometry in such a way that demixing occurs. So the difference in scattering length drives the two components of the condensate to separate from each other, as shown in these time-of-flight images here. You see that the state 2 stays in the middle, state 1 segregates and goes to the periphery of the trap. And because we're using a pulse to create the superposition, this is a dynamic situation. So actually, this outer component does this and then swings back to the center. And in order to get to now drive a second transition, of course, you have to do it in the right moment, because you have to do it in a moment when the two components overlap, which is how this time of 1.1 second comes into play. Indeed, when we look at the contrast as a function of time, you see that it first goes down and then goes up again, just as you expect when you look at these images here. And in this graph here, the contrast revival, it goes up to about 90%. In the meantime, we have achieved up to 96% of contrast for this revival time. And at this revival time, then, what limits the squeezing? Well, this time it's losses. Losses in the system are asymmetric. It's not the same amount of loss in the two states, and they introduce noise, and this noise counteracts the squeezing, and so this is the limit of the process. But we haven't, so far we have only tried it in this particular trap, and of course the question comes up of how far you can go, how far you can optimize. This is actually really only the first, these are very, very recent results, and we don't know yet how far you can drive this squeezing. There has been a theoretical prediction of 6 dB in this article here. Alice Sinatra at LKB has done simulations where it turns out that this is extremely sensitive on the scattering length, of course, because it depends on scattering length twice, right? The demixing depends on the scattering length, and then the squeezing depends on the demixing. So that makes it difficult at this time for us to predict how far we can go with that. I think that the trap aspect ratio plays an important role for that question. Is it good for something? Well, we don't know yet, but let us know, though, that although BECs are not a good choice probably for clocks, they do appear as source states in atom interferometry, and so that might be interesting in that context to know whether this squeezing can be pushed to more sizable levels. With that, I'm at the end. If you want to know more about this, there's a poster today by Theo Lodin, and let me acknowledge the marvelous group who did all that, and in particular I'd like to mention Giovanni Barontini, who led the Zeno experiment, who is here, Romain Long, who is leading the effort of the quantum gas combined with the QED experiment, also has a poster and also is here, and Theo Lodin, who did the squeezing experiments in the TAC clock experiment. Thank you for your attention.
It's a fascinating talk. Thank you, Jakob Reichel. So now we have opened the questions, so we can have a few questions.
One.
For your very nice experiment on the Zeno blocking the ground state and making this Wigner function of a hole, in theory, when you improve your cavity, how does the fidelity scale with the cooperativity of the system if you ignore the higher order modes?
Okay, I don't exactly know how the fidelity scales, but the spontaneous emission, unfortunately, scales with 1 over c, not 1 over c squared.
Thank you.
So, yeah, maybe I can add, we of course looked a bit into what other states we can produce with that scheme, and it seems promising to go a bit away from the pole, and you can probably produce with considerable fidelity some of these higher Dicke states. However, when you come close to the equator, at least with foreseeable improvements in technology, I think it's not realistic to produce Schrödinger cat states. The reason being that in that case, as you move towards the equator, to block the equator, you have to use a fairly detuned cavity, and so then the cavity response is no longer as steep as it is now. So you will have some states that produce some intracavity intensity, whereas now we have this all or nothing situation, which is very favorable.
Wolfgang, yeah.
Jakob, I wanted to ask you about the last experiment where the interactions create squeezing.
Yes.
I haven't fully understand to what extent this, I would call it, buoyancy-driven oscillation is necessary or not, because there is a tiny difference between the scattering lengths, and over 1 second, maybe this would result in squeezing by itself?
No.
So my question is, if you had a box potential without any harmonic confinement and the system would just stay in a homogeneous state, would the small difference in scattering lengths in rubidium?
No, it would not be enough to I don't know what the time scale is, but it seems to me that we looked at the values and it was hopeless to see it without the phase separation.
Okay. Other questions? Okay, if no question, let's thank all speakers again. So we will close the first morning session and thank you all of the participants to attend the first session. Thank you.
Okay, I have a few announcements, please. Concerning the tomorrow afternoon DMZ tour, there is a limit to the number of attendance for the DMZ because not many people can enter the infiltration tunnel together at the same time, which is part of the tomorrow's tour. So the priority will be given to those who have registered online before the conference. So please sign up in the front desk to get the coupon which you need with your passport to get on the bus tomorrow. And if you do not sign this morning, during this morning, the seats will be given to others who wish to join the tour. And we also have the group tour tomorrow afternoon, or you can have free time wherever in Seoul. And also, we have 3 options for the food for the Thursday banquet. If you do not want to have the Western food, you can choose either the vegetarian or halal. So please sign up your preferred food. And for the coffee break, we have the few more stations outside this auditorium in the lobby. Please do not go down to first story or other place. So please enjoy the coffee break. Thanks. We'll start at 10:45.